I'm now pleased to introduce our speaker for today's webinar, Engineer Ahmed Gaber. Engineer Ahmed is a senior petroleum engineer at the Gulf of Suez Petroleum Company, GAPCO. He joined GAPCO in 2012. He has over 8 years experience, including an offshore exposure. He got his bachelor degree in petroleum engineering from Suez Canal University in Egypt, 2011. Engineer Ahmed presented a couple of technical papers in Egypt Petroleum Show, Egypt, in 2019 and 2017. He volunteered as an instructor for gas lift and well modeling using Prosper for both SPE Egypt and Petroleum Development Program in Egypt. He was a technical manager for the Society of Petroleum Engineers Egypt section for young professionals in 2017-2018 season. Welcome, Engineer Ahmed. Thanks for being with us today, and I will turn over to you to begin.
Good afternoon, ladies and gentlemen. It's a pleasure for me to share with you some of knowledge about nodal analysis and some of its application through online Petroleum Academy, OBA. I try to make it to the point because I know that most of you are interested more about the practical application rather than equations and theories. So I will start first with contents. We will speak about nodal analysis in brief. Then we will go to well performance component, IPR curve calculation, VLP curve calculation. Then we will go to system analysis and see how we diagnose different problems. And finally, we will go through many examples using Prosper model, and it will be interactive step by step. I hope that you all get the maximum benefit from this session. So, nodal analysis. This is a fundamental concept of nodal analysis. As we see here, there is a segment. In this segment, we have a pressure here known and another pressure here known. It's a node and this is a node. Across the segment, in the intermediate, we have a solution node. So as the solution node, it's required to know what will be the pressure for a certain rate. But before we go through this, we have to know into our concept that the component upstream of this node is the inflow, and the downstream of this node is the outflow. And for sure at this node, the QN is the same as Q out. So is nodal analysis only used in petroleum engineering? It was interesting for me when I Google it and first write down nodal analysis that discovered it's first related to electric circuits. And if some of you remember what we studied in electric circuits, you will remember Kirchhoff's law and how you are doing nodal analysis to know what is the certain resistance or certain capacitance of a certain segment. So here I write down some of the applications of nodal analysis that I actually use in my company, in my work many times. So if you have to drill a new well, a development well, how do you think you will know whether this well is economic or not? You drill the well, you spend a lot of costs, like millions of dollars, and you want to know, will the return on this cost will be beneficial or economic or not? So to do this, you have to know what will be the production from this well. So modeling and nodal analysis helped me to know, as we will see later, what is the initial production of this well. And reservoir engineer can take this production and he can do some decline analysis on this production and estimate what will be the reserves of this well. Then you want to know what will be the future performance of this well. For example, now you have a 4,000 PSI reservoir pressure, and you know that by time it will decline. So what will be the rate after 1 year or 2 years from now? Or on contrary, if you are going to do some water injection or gas injection project, you want to know what will be the performance, what will be the gain from this job. Also, as we will see later, Using nodal analysis, you can optimize your completion size. Use your wider completion or smaller completion. Also, what will be the artificial lift you use? Do I need artificial lift originally? You need artificial lift or you do not? And if you are going to use artificial lift, what will be the optimum parameter of this artificial lift? And also controlling the optimum rate. So sometimes there are constraints regarding the pressure drop across the reservoir or across the flow lines or across the completion itself. Sometimes you are constrained by a separator at certain pressure. Sometimes you're constrained by a certain pressure drop across the reservoir because, for example, you are afraid of sand production or you are afraid of water cooling or whatever problem. And also, from the most common application of nodal analysis is to diagnose the system for any problem. Is there a problem in the reservoir? I need like do some reperforation or need the stimulation or whatever, or there is a problem in the completion system itself. Okay. This is a quick diagram showing the production system. As we see, it's all start from the reservoir. I have a reservoir pressure which give energy to the reservoir fluid to move through the reservoir until it reach the well bore at the sand face. So this is the drawdown, which is the difference between the BR, reservoir pressure, and the BWF, bottom hole flowing pressure. Then the reservoir fluid is moving up across the completion, the tubing with its accessories, if it's have like some nibbles or anything, until it reach upward till the tubing head, the Christmas tree. And then it move from the wellhead to the separators or whatever the protection facilities through some flow lines and the choke if it's required. So as a petroleum engineer, I'm concerned with the pressure drop across this system because this pressure drop and this system I can use to optimize the maximum flow rate and the maximum revenue. My concern now will be at this node, this solution node. So remember, we said that in a solution node, we have the inflow, which will be from the reservoir to this point, to this solution node, and the outflow, which will be through the completion system, as we see here. So at this node, let's start with the IPR, the inflow from the reservoir to the bottom of the well. As we can imagine, fluids are moving through this media. So this movement or this flow is affected by many parameters. First of all, it will be affected by the fluid characteristics itself. A denser fluid for sure will make or will experience pressure loss more than a less dense fluid. A high viscous fluid will experience less pressure drop compared with a less viscous fluid. So, as we will see later, it's important to do accurate simulation of the reservoir fluid, which can be done through data from analog wells in the reservoir. The second parameter is the rock properties. Movement through this is affected by the media, the porous media where the fluid is moved. So, higher permeability reservoir will be less pressure drop than low permeability reservoir. And I don't know if most of you are familiar with the term skin or not, but skin is mostly related to the completion design at the interface with the sand phase. Whether you are using an open hole completion or slotted liner or cemented and cased hole, and what is the deviation of the well compared to the reservoir and stuff like this, and this affecting the skin and the pressure drop into this area. Then there is the flow vertical lift performance, which is the flow through the casing tubing to the wellhead, which is logically affected by the fluid characteristics and the completion design. This is the core of nodal analysis, and this is you will be very feel a lot of surprise that most of our work is based on these two curves. If you understand these two curves well and understand different sensitivities related to these two curves, you will be a good petroleum engineer, and you will understand what's behind most of things. So this is a relation between the pressure and the rate. This curve, which is the inflow performance relationship, show the drawdown as a function of the rate. It means as I increase the drawdown, I get more rate, and we will see this, and we will get this later. While the vertical lift performance curve is showing the required bottom hole flowing pressure that is capable of lifting the reservoir fluid into the surface. We will come into each one in detail in the next slides, but the important thing is that the intersection between these two curves is the solution of the node point, which give me the rate, only one rate, and this rate is accompanied with a certain BWF. So this is the IBR curve. As we said, we will go through detail. First, at this point, if the BWF is the same as the reservoir fluid, this means there is no drawdown across the reservoir, so there is no flow. But as you decrease the BWF, this means you are increasing the drawdown. The drawdown here is the B reservoir minus B1, the BWF1. And so increasing the drawdown more, you will gain more rate until we reach the absolute open flow, which is theoretical. That is the maximum flow rate that you reach when the drawdown is maximum, when the bottom hole flowing pressure is equal to 0. There are a lot of IBR models. These models aim at drawing this curve. So the first model, which is PI entry, which is the simplest model, is taking this curve as a straight line extended here, and using this model, we can draw simple IBR model. It's only a number. And then you go into more sophisticated or more complex models where more data are required. I will not go in details through this because I'm concerned more about the exercises and about the examples that we are gonna go through it. But for me, you can see here that each model requires different set of inputs, and it's going from being simple to being more complex. Here an example. This is the screenshot from Prosper model, which we will speak about later. And as we see here, I wanted to draw this curve, the IBR curve, using Darcy model. Here, this is the data. I use this model because I already have this data. I have no problem with this data. Based on the available data, I can go to another model. So here, as we see, it is the reservoir permeability, reservoir thickness, drainage area, shape factor, and the wellbore radius and the skin, and I used this to draw this curve. So now we finished the first component. Now with the second component, the fluid loss, the fluid pressure loss across the wellbore. As the fluid move across the wellbore, it has pressure loss, which is come from three factors. The gravity, and it makes sense because you have density of a fluid and you are going or pushing it up against the elevation, the normal potential energy. And there is a friction because fluid move and making shear stress and friction between the fluids and the tubing wall. And the last factor is the acceleration. However, it's minor and it's not that much, and it's due to the fluid expansion with pressure reduction. And as you see here, the curve showing the component. And this, if for example, we have a pressure loss while the fluid is moving up along the wellbore, and you divided it into its component, you will see that here is the component of the gravity. And as you see here, first it decrease, then increase here, and we will come to this later, is unstable region. And this is the friction pressure loss, which is increased as the rate increase, while this with minor effect is the pressure loss due acceleration. So this pressure loss is affected, as we said, by many factors. These factors are affected by the flow regime along the pipe. I tried to make it simple here, and I brought only some flow regimes through a vertical pipe, which will be different if it's slanted or it's horizontal pipe. So normally, and this happens, that at the beginning, the gas oil ratio downhole at the wellbore is not that much. So the continuous phase will be most likely the liquid, while the bubbles of gas will move through the fluid. While as you go up, expansion happen and the gas expand more, and you will see that there will be a slug shape. Then it begin to connect it more into churn shape, and it end with the annular flow or the mist flow, where the continuous fluid became the gas. And the friction loss is dependent on what is the regime there, due to certain things like the slippage velocity, but I will not go through this here. And as we have models for the IPR, we have models also for the VLP. And here is a lot of models, like Dance and Ross Original, Dance and Ross Modified, Fanshawe Brown, Petroleum Expert 2. Each model have like a region where it's working the best. So here I wanted, using Prosper, to show you what's happened. This is a well. I have the wellhead pressure, the first node pressure. Wellhead pressure is 250, and the water cut, and gas oil ratio, and I have the rate. So as we see, as we go, you can go from here or there, but I will go from here. If I have the BWF, which is equal to around 2,600, as I go up, there is pressure loss. There is pressure loss. This pressure loss is combined by this rate, this gas oil ratio, this water cut, until I reach to the surface. So if I change it, any of this parameter, I will find out that this curve will change, which means the pressure drop will be different. So we can think about it. What if I increased the gas oil ratio? Now start from here. I have the same rate, the same water cut, and I changed the gas oil ratio. Do you think the BWF will be higher or less? The BWF here means it's the pressure loss I need for this rate to reach the surface. So here's the example. This was 500 standard cubic feet per barrel, and when I increased the gas oil ratio to 1000, we see here that pressure drop is less, which means I need less BWF, which is the idea behind doing gas lift injection. So what is VLB? VLB is a mixture of this pressure traverse, which means for the certain gas oil ratio, for the same separator pressure or wellhead pressure, for the same water cut, there is a relation between the bottom hole pressure and the rate here. And as we see, I need a certain pressure for certain rates, certain BWF. Let me stress into this again. I have already a wellhead pressure, a known wellhead pressure. It's constant, for example, 250. And I have the same gas oil ratio. And now I want to see when the rate increase, what will be the BWF. So this is the VLB. Actual VLB is like this, because if you remember, I mentioned before that we have two regions. We have the unstable flow here, and this region is mostly affected by the gravity factor of the pressure loss, until here it's more about the friction loss. So here it's increase, the pressure loss increase with increasing the rate. So now I know about the IBR curve and how to draw it, and the same here, I know about the VLB and how to draw it. And logically, the pressure drop to be drawn through the VLB, I need to know the deviation survey, I need to know the completion details, the tubing size, any diameter change, any wall roughness, and this is getting me into the final product, which is the system plot or the nodal plot. So, as I mentioned at the beginning, one of the applications is to calculate the production rate from the well. So I have the IPR and I have the VLB, and the point of intersection is the flow rate and the BWF. I can do sensitivity for each component. I can use sensitivity or change the parameters in the reservoir and see what will happen and what will be the rate, or change parameters along the completion and see what will happen and what will be the rates. For example, the reservoir pressure is declining. So I want to know, wait a second, this question. Okay, I will answer most of your questions after finish, and I think inshallah we will have good timing for all questions. So as we see here, this is the VLP, and as we said, we want to see the effect of declining the pressure on the system. So declining the pressure is not related to the VLP at any time, it's related to the IPR. So this is the original reservoir pressure, and then the reservoir pressure declined into this. So I can understand now what is the initial rate and what will be the rate when the reservoir pressure decline. And this, as we will see later, can help me to diagnose certain problem happening. For example, there is a decrease in the rate. Is this reduction because there is a problem in the reservoir, or it's problem, or it's normal decline reservoir pressure? The same for the VLP. For example, I was forced to use a wellhead pressure, a high wellhead pressure, for example, 3000, because there was constraints into the flow lines or the separator, or I do not want to open the well because the reservoir engineer is afraid from sand production or water cooling. And after some time, I don't have the same constraints, and I want to open the well more and decrease the wellhead pressure. So I want to know what gonna be the rate. And as we see here, it's a sensitivity plot showing it can be done for the wellhead pressure, it can be done for the gas oil ratio, for anything, to see the effect of each parameter on the total rate. So for me, I finished what I want to say as an introduction, and I'd like to speak now with example to show you what we have been through. I will go quickly to see if I can answer any of the questions now. Okay, I will speak about the stable and unstable operating point, and I will speak about all this, and it will be easily through the model. So now I will go into Prosper. So what is Prosper? Okay. To do this nodal analysis, normally you can use Excel sheet and do it. There's no problem. You have the correlations, you have the equations, and you can use various equations, various correlation to do this drawing of the VLB and of the IBR. But in the petroleum industry, we have certain programs to make life easy. You have the most known programs are Prosper, which is under the Betex company, Petroleum Experts, and there is PipeSim. And as we will see now, it's easier interface. It has a lot of data inside, like you have data casing database, tubing database, you have a lot of things, you have artificial lifts base, and it can do sensitivity very easy. This is the interface of Prosper. If you have been working into Prosper before, you will find it has different version, but mostly it is this. The differences are not very much. This is the option summary where I define the system. I define what is the fluid I'm dealing with, what is the method of the BVT, what is the status of the separator, is the well is tubing flow, is it producer, is it injector, if I have artificial lift method or not. Here I can write certain information. Then I will go quickly through this, okay? Then I can speak here about the calculation type, the well completion, it's cased hole, open hole, I have sand control or not, I have gravel bag or not. What about the reservoir? It's multilateral or single branch. So this is a quick option summary. It's like defining the main things about the model. Here, it is the BVT section. We mentioned before that it's very important for us to define precisely or accurately the fluid down there, because it's a main factor to calculate the pressure drop across the reservoir and also across the well bore. We know that mostly we are having two things, either like you are using a black oil model, or you are using like equation of state, volatile oil. You have many models. Here in Prosper, it's easily to enter the input parameters, that the fluid type you have and the fluid properties, and you can do matching and using correlations here, which is not our requirement now, and define the fluid you are using. Here we have the section of the IPR. As we see, this section is defining the inflow performance relationship. It's identifying the IPR, and as we see, we have different models depend on what is the input we have. Darcy, for example, it will require the reservoir mobility, thickness, and all this stuff, and the skin you are entering by hand. However, if you are using a different model, like Phoenicia, for example, you will find that you will need a relative permeability of the oil. I'm going quickly through this because it's not our intention now, but I try only to give you some flavor of everything. So here, the equipment data. And as we can imagine, this section is important to draw the VLB. I need a deviation survey. Okay, here's a simple deviation survey, but normally we have long deviation survey with with change in angles, but here it's only like vertical angle for simplicity, vertical well. And then also we have the downhole equipment. I can like draw it to you. Like this is the wellhead pressure, this is the tubing, and this is the casing. Here it's simple, but it can be more sophisticated or more complex than this. And finally, I enter here, I enter the data in the IPR, and I enter the data in the VLB. And now I have my VLB and I have my IPR, and I can do my analysis. So the first thing for analysis, let's imagine I have this well, which is like development well. The reservoir engineer gave me certain data. This data here, he gave me the reservoir permeability, the thickness, all this stuff, and he gave me the skin. And I enter here, and I calculated and drew the IPR. So now I have the IPR of the well, which define the productivity of it. And then I enter the deviation survey, the downhole equipment, geothermal gradient, and all required data. So I have the VLB curve. I can draw to you the VLB here, but without any variables. And now I have my VLB. So now I can easily estimate what will be the production rate of this well. I come here, I put my input data, what is the top node pressure, what is the water cut, the GR, what correlation I will use, and then I can easily do the calculation and get the rate here, the liquid rate, the gas rate, the oil rate, water rate, what will be the BWF, and I can plot this to show you here what we have. So, as I mentioned, we would like to do some analysis. We want to know, for example, what is the optimum tubing size to be used. So I can do this easily here. I can go to the system and change the variable. For example, I will change the tubing pipe diameter. I will use different tubing pipe diameter and see what will be the rate. I think most of us think now wider tubing will be better. And as we see here, is the change in the VLB as we go from here. Wait a second, I want to show you. Yes. Here, as I move here, you can see the x-axis and y-axis numbers. Data. So this is the number 0. It is the smaller tubing size. We will see we have rate around 4,600. Then using higher, bigger tubing means I have bigger rate. And as we see, then using bigger and bigger, there is not that much effect on the gain of the production. So always, or most of the time, we are doing compromising here. We are doing optimization. Bigger tubing size mean more cost, but in the same time, it mean gain in oil production. So you are quantifying and seeing, is the gain equal to or higher than the cost? So I will go through this direction. Another example that I would like to show to you is to expect or estimate what will be the rate assuming different reservoir pressures, as we see here. Different reservoir pressures give us different rates. Declining in the reservoir pressure, meaning less rate, as we see. I can enter another number. I can enter here, for example, lower number, like 2,000. And I want to see this because I want to show you something. You see here, there is no intersection between the VLB and the IPR, which means that at this case, there is no production naturally from this well. So in order to produce, I need some artificial lift method if I have to deal with this reservoir pressure, or I have to do some water injection or gas injection to rise this pressure to intersect the VLP curve. Another example that I will show to you, it's like diagnostic example. It's the same model, but the difference is that I entered certain data. Imagine you have this well, which was you already at the beginning, you made a modeling for it. And after some time, you find there is a reduction in the flow rate. And you went down with a pressure gauge, and you could have this. You could have the liquid flow rate, and you could measure the BWF or the pressure. So you want to understand, is it the normal behavior or normal performance of the well, or there is some problem and some actions are required? We will see here this during sensitivity of the inflow. First, this was the original IPR of the well, and then I have this test data. So at the beginning, I changed the reservoir pressure to see what will be the reservoir pressure to pass through this test point. So I found in order to have this rate, then there's a reduction in the reservoir pressure to be like 3,750. So if I have this reduction, I go to the reservoir engineer and I have speak with him, and I asked him if the reservoir pressure already decreased, So if there is a reduction, so it's normal. So nothing is to be done into the well. But what if he told me, no, that's not right. The reservoir pressure didn't decrease and it's the same. So at that point, I will change the variable or the diagnostic variable, and I can suggest that there is a reduction or change in the skin. I did analysis and I go and I calculated and I found out that there is increase in the skin. This well had like a 2 skin, a skin value of 2, and now it's increased into 5. So this give me a way to say that I have a problem here and I need to remove it. And then I can think about the best way to remove this problem, either by like doing pre-perforation or like doing stimulation or hydraulic frac or whatever. The last example I'd like to show with you, and after this we can like talk freely and answer questions, and if we can do another example, we can do it, no problem, is to show you the effect of doing artificial lift. How I can here model the artificial lift, how I can see what will be the gain of using artificial lift. So as we see here, this is the variables. Here I changed the variable. I changed this well to use, for example, I will not do gas lift injection, or I can like do gas lift injection with various injection rates. And I plot, and I can see here the change or the increase in the rate as I increase the injection of the gas. I will illustrate it in a better way. I will use here the sensitivity, and I can change the variables. As we see here, I have a liquid rate of 9,600, and while I increase the injection gas, I have increase in the rate. So as it is it, yani when I increase the injection gas, I will keep increasing. The rate will keep increasing? For sure, no. I can here use high rates to show you. As we see here, that at the beginning, increasing the injection gas will increase the liquid rate, then there is not much increase in the liquid rate. On contrary, it will begin to decrease. So for me, this is what I wanted to share with you today. As I told you, I tried to make it quick and to the point, and I hope that you all have learned something from this. And now it's with Hassan until I like read the question and see what I can answer from them. Thank you all.
Thank you, Engineer Ahmed, so much for your wonderful presentation. At this time, I'm going to the questions and answers segment. If you like to ask a question, please go to the Q&A box in down screen, in the down part of your screen. Type your question in the Q&A box. Please make sure you click the send button so that we got them. I will go now to the questions. So please forgive me if I'm pronunciation for your names maybe sometimes maybe terrible. So okay, the first question from Hamza. Hamza Ahmed is asking, do we perform a nodal analysis in association with the well test data?
Yes, normally we do. Yani normally in this model we have test data. For example, at the beginning, I have data from the reservoir engineer, from which I draw and calculated the IBR curve. Then, so I put the data and I put the data of the IBR, and then I have new test data. I will make calibration of the model. I will make calibration of the, for example, the flow correlation that is used to calculate the pressure drop along the well bore. So for sure we are using it, and maybe inshallah if we have another session, we can go back into details to show how is this happening, and how is you start from theoretical way with the data you have, and then you calibrate it to the actual data.
Okay, great. Vosal Iskander is asking, are we considering the stable and unstable points in matching our IBR?
Are we again? I reading. Let me. I'm reading here the question. So this is the same question as you said, that visual Iskander.
Yes.
Or is different?
Yeah.
The same.
Yes.
Okay. So you are asking. He is asking about if we're gonna do. Actually, it is into some equations, and I do not want to go through it in details because it will take a long time. But normally, what we can speak about it, that I will show it quickly in this presentation. If you remember this, we speak here about the component of the tubing pressure drop. At the beginning, you see here, it increase, the pressure drop decrease, and it's mostly about the gravity factor. And the problem is related to the flow regimes and the change in flow regimes and stuff like this. After this point, the gravity is normally, it's like the same, there's no much change. But here, the friction increase with flow rate. So if, for example, what will happen? If, for example, I want to show you. If, for example, there is intersection between the IPR and the VLB at this point, you will find this, there is a region of instability. There will happen like loading up, and you will not produce the well in a stable manner. And I already experienced it before this situation. We had a well, this well was into the margin, it was very near to the unstable region, and sometimes with a very small increase in the water cut, it's become into the unstable region and it's loaded up, and its performance change until it stopped production. So what we happened in this situation, we increased or opened the choke of this well and increased the rate to be into the stable region. I hope I answered this question. Okay. So what's the next question?
Great. Another question is asking about what are the main factors that affect the flow regimes?
The main factor affecting the flow regimes, okay, there's correlations that showing the flow regimes, but the main factor is the quantity of gas and the quantity of oil. For example, if we have oil and gas together, what is the quantity of oil compared to the quantity of gas? And also the density difference between them. What is the density difference between gas and oil? Because mostly flow regime, it's about the slippage or the difference in superficial, which I'm going to speak about it here. Normally, when we have a water cut of 50% at the surface, okay? So we imagine down there at the well bore, it will be also like 50% oil and 50% water. It's not the case, because normally oil is faster than water because it's less dense. So if it's a surface, if at 50%, you will find that down, it will be like 70% water cut. This is the term of the hold up that is different from the water cut. Hold up is different, completely. from what you mean by injection data. يعني what you know.
Okay, I think Hisham, you have to define your question more. We will move to the next question. So Balash is asking about what is the meaning or the definition of superficial velocity.
Yes, superficial velocity is the velocity of the fluid if it, يعني for example, as I said, when you are measuring the velocity of the mixture or the velocity of the fluid moving along the wellbore, you are measuring the mixture velocity. But each phase have its own velocity. Superficial velocity, when we say that, for example, you have a wellbore and we say that only oil is moving there, so this is the superficial velocity of the oil, or it's only water that's moving there, so this is the superficial velocity of the water. And this I need like some diagrams to show you to this. So if you are interested into getting details, maybe like we can do some session if people or attendees is requiring this, and we can show with correlations and with equations and with some diagrams everything related to this.
Okay, the next question, Ahmed is asking why the VLB curve began with high reservoir pressure value, then decrease to make loop, I think, then up again smoothly up to the end.
Okay, as I think Ahmed now may be knowing the answer because we answered it when we were speaking about the unstable region. That at the beginning, again I will show it to you. I will show the curve to you. At the beginning, here the main factor is the gravity, and here how to I will illustrate it or explain it in an easier way. It's like you have oil and gas or oil and water, and oil is moving fast, but it takes some droplets of water with it, and then it's fall down again because the velocity is not that high to take the whole stream without any problem. Something like this. So at this part, the gravity is factor effect very high and is not stable. But starting from this point, it's now mainly about the friction part. So that's
okay, great. Khalid Hussein is asking, does it possible if we haven't or we don't know about the flow rate from surface that we can find the nodal analysis?
yes, for sure. Sometimes I will tell you something. That's I'm using a lot in my company. Sometimes you have a well and this well cannot be tested for any reason. For example, the test line is broken, you have a problem, okay? So you have your model, you can, for example, the current water cut, the current gas oil ratio, the current reservoir pressure, everything, and you can do system analysis using nodal analysis. So it's possible, yes.
Okay, we will move to the next question. Faisal is asking, does the solution node or point at which curves intersect tell that this will be the rate and pressure at given completion design?
Exactly, Faisal. Exactly. You get into the point. This solution point intersection tell us this will be our rate and pressure. And when you change any of the parameters, any of the, for example, the water cut, you change the IBR, you change the reservoir pressure, you change anything, you will have a new intersection point.
Okay. Abdul Qadir is asking, I wanted to know why in your inflow and outflow diagrams, the outflow curve goes down and then goes up. Engineer Ahmed, can you hear that? Hello? Hello?
Yes, yes, Hassan. I'm answering your question.
Okay.
I'm answering Abdul Qadir question. So Abdul Qadir question, I think I answered before. It's about why the VLB curve is moving down and then moving up. And as I mentioned, it's because first it's gravity dominant, and then it's friction dominant. Hello?
There is another question.
Yes.
Can we elaborate the digit shape factor?
Can we what?
Elaborate the shape factor for our well.
What you mean by elaborate? You mean calculate, you mean?
Maybe.
Yes, we can calculate it. You know, in Prosper, I will show it in Prosper. That's why I'd like it to open Prosper, because some questions can be answered here easily. Here, in Darcy model, wait, input data. Here, something called calculate tides shape factor. When you enter here, you tell the model what is the location of the well related to the nearest fault here or reservoir boundary, and you specify or enter the data of each parameter, and you can calculate the site shape easily. You can do it here. For example, here is the width is 1000 and the length is like this, for example, and we done. You see, this is changed. So we can calculate it easily, because in Prosper there is correlations that it's used to calculate whatever variable you want. Yeah, no problem regarding this. So what's the next question?
We actually have many questions, but we will try to answer a couple of questions because we are running out of time.
No problem.
Caesar is asking, any example using artificial lift with electrical submersible pump or other artificial lift using pumps? I think that may be in another session.
Yes. Actually, we can do another session if people are interested to go.
Yes, it's possible.
Through.
Okay. Azam Aziz is asking, why in the IPR and VLB curve the intersecting point is the optimum parameter? Is the optimal parameter?
What you mean by optimum parameter? It's not the optimum parameter. You can make it the optimum, but the point is, as we said, from nodal analysis, you have the same inflow, the same outflow. Yani at a certain point, it must have the same pressure and the same rate along the point. So it's not the optimum. It is the, and how to say it? It is at this point the reservoir can deliver this rate with this pressure, and along the wellbore, I can use this pressure to deliver this rate. So the intersection is the value at which both segments intersect, the value at which I can produce.
There is another question from Abdullah Muhammad asking about how skin can affect the flow regime.
No, skin is not affected with the flow regime. First of all, skin can be, it's along the interface with reservoir. It's not across the VLB. It's at the completion, the intersection between the completion. Wait, I prefer to show it in here. When I speak about skin, I mean this part, like the interface between the completion and the reservoir, the sand phase. Skin can be due to various reasons. For example, as you see here, I have a slanted or a perforation here. So sometimes this perforation is plugged, so there's a skin. Sometimes the well here is deviated, so I penetrated long distance into the reservoir. So means there's the streams of the fluid and pressure converge or diverge, so not much pressure loss. For example, I have a gravel bag which is making some skin. So skin is here in this. Flow regimes is here. So skin is not related to the flow regime. You can say it's related to the way the fluid is moving here. I mean, the fluid is passing through a small area or big area. You know what I mean? But flow regimes and this slug flow or bubble flow or these things is not related to the skin here.
Okay.
So what's the next question?
Ahmed Rashid is asking, what is the correct procedure to prevent sand production?
Okay, the correct procedures, there are curves that you enter. You see, I have, for example, the probability of the reservoir. There is a value called UCS, compressive strength of the sand. And using this value and this permeability and using the it's unconfined compressive strength, okay, we can know this value from sonic logs. So you know these values and you enter to certain diagrams and they give you, like, if you exceed certain drawdown, you will have sand production. In actual case, in my company, there is a well that you cannot exceed like 600 or 700 psi drawdown, or you will have some sand production. So we did our best to control it from the surface, to have some choke and increase the wellhead pressure to control it, so we don't have a drawdown greater than 400 psi as a safety factor. What else?
Okay, great. This will be the last question. Sherry is asking, at what point can we consider the well not economically viable for production?
At what point we can consider the well is not valuable to production?
Yes.
Okay. This is based on the cost and the revenue. You know, it's good to end with this question because it's actually a nice question. You have to put into your consideration that the core of our job is revenue. You have to produce oil, sell this oil, get gain. But producing this oil is costly. You have to make some cost to produce this oil. So when the cost of producing reaches, or it's higher than the cost of selling this oil or producing this oil, then it's not economic anymore. You are losing. You are not adding a value to your work. For example, what we are doing, for example, I have a well, and this well having a problem, okay? And to remove or solve this problem, I have to make a workover. Workover is to bringing a rig into the location and change the completion and put another completion. This can cost like $3 or $4 million, okay? So I make some economic analysis. I see how much will be the gain from this one, how much gonna be the reserves, and does it cover the cost or not, and when will be the payout time. At that time, if I did all this analysis, I go to my manager, I tell him, please give me $3 or $4 million, and I will give you this gain with these risks. And that's all.
Actually, we have so many other questions, but we are sorry that we are run out of time. So for now, thank you, Engineer Ahmed, for your time. Thank you so much.
Thank you all, and really, I'm very happy, and I'm very happy about your questions, because this means that you were interactive and that it was an interesting session. And I hope to get your feedback. And if anything is not covered, we can have another timing together to cover anything. And really, thank you all. Yeah.
Thank you. Thanks to all our audience for their participation, but we must end. But before we end, please take a moment to fill in the feedback survey that is in the chat box. We do rely on your opinion to improve our services and offering. Have a wonderful day. Please take a moment to fill this survey. We look forward to seeing you all in the upcoming webinars very soon, and you may disconnect now.